here. Looks like someone stole the lapel microphone. So I have to use this. If it has a rock band or something, it might have done. All right. Does anyone have any questions about anything before we start? Any questions? All right. Assignment 4 is due soon. So what we've been doing is looking at decision networks recently. And the idea is that the decision network, there's 3 types of nodes. There's decision nodes, which draw as rectangle, random nodes, which we draw as an ellipse or a circle, and utility node that's a diamond. There's a range. Each of them have a range, which is a set of possible values, but only for the decision and random variables. The utility variable doesn't have a range. There's a unique utility node that specifies what our value is. Now the arcs into the decision node represent the information that will be available when the decision's made. So this tells about what information we will know when we make a decision. And for each random variable, there's a factor representing the conditional probability of the random variable given its parents. So the factor for every random variable. And there's a factor for the utility, and the factor for the utility is a factor on the parents of the utility node. And there's no factors associated with the decision nodes. Okay, any questions about that? Okay. So what I'll do now is we'll do some quicker questions. This decision network requires which probabilities to be specified? Oh, so this is about buying a car. So some cars are called lemons, right? It means it's a car you don't want to buy. And you can do a test on it, and then after the results, you can buy something that's utility. That's what lemon means here. Okay, anyone need more time? Does anyone still need more time? 3, 2, 1. We'll stop. The answer is D. Oh, only half of you got that. Okay. There is no probability of the utility. There's a futility function on this. There's no probability of the utility. There's only probabilities of random nodes given their parents. What was B? There's no probability of the tests or buy. There's no conditional probabilities for testing or buying. Right? There's no conditional probabilities for these decision nodes. Okay, there's only the probabilities of each random variable given its parents. Any questions about that? This is the same question as last time. I just changed the graph slightly. Okay. Next question. The decision network requires how many factors to be specified initially? Okay, how are we going? Does anyone need more time? Okay, 3, 2, 1. Yes, it requires 3. Does everyone understand why it requires 3? There are 2 conditional probabilities and the utility function. Any questions about that? So that's all the factors. There's always one more than number of conditional probabilities. I want to know here about the initial probability that isn't a conditional probability, the initial factor that's not a conditional probability. It's a factor on which variables? There's three factors. We've seen two of them. They're the conditional probability. What's the other factor a factor on? All right, does anyone need more time? A bit more before. Oh, that's better. It's speaking up. Okay, 3, 2, 1, stop. Yay! It's the utility function. It's a function of lemon and bi. There's still... Oh, it's only 50. There's still a number of people who are getting this wrong. So D, it's not a function of test. There isn't a factor on test and bi. There is a function of the utility. And that's the remaining one, right? There's a factor for every conditional probability table and a factor for the utility. What was C? There's none for test and bi. There's one for the utility which depends on the lemon and the bi. Okay, so there's factor for every conditional probability table and a factor for the utility. Okay, are there any questions about this? All right. So, next one. This is now different. The last one was the same as last time. Here's a new one. So according to this network, when does the agent know the value of result? So it's the same network. And the question is, when does the agent know the value of result? Does it never know the value of result? Does it know it initially? Does it know after test and before bi, after bi and before test, or after both test and bi? All right, okay, anyone still need more time? 3, 2, 1, we'll stop. Yay! Right, so it learns the result after test and before bi. That's what this means. Okay? Any other questions about this? So that's what these arcs mean. And last question. Same question as before, except when does the agent know the value of lemon? According to this network. Okay, anyone need more time? Okay, 3, 2, 1, stop. Ah, that's interesting. The answer is never. It doesn't initially know it, just like it doesn't initially know the result. You don't know whether it's a lemon or not. You only know, everyone got the previous one right, so I'm just wondering, this seems, you only observe the things, your parents. Right? That's the only thing this agent observes. It observes nothing when it does test, and then when it does bi, it knows the test result. That's the only thing it observes. The answer here is never. I'm surprised everyone got the previous one, didn't get this one. Anyone have any questions about that? Lots of people got it wrong, so it's the only thing we observe is what's the parents of the decision node. This never gets to observe in this what the lemon is. Any questions about that? Okay. All right. What we're going to do today is we're going to look at these decision networks. We're going to work out how to compute the optimal policies about how to actually find out what the agent should do based on its model and its utility function. And then we're going to do something called the value of information. We're going to work out how much information is valuable to us, how much it's worth to us, and the value of control, about how much would it be worth to actually control some variable. So first we're going to do is we're going to define something called a no-forgetting decision network. It's a special type of decision network. And it's the sort of decision network that we can solve efficiently. So it's a decision network where the decision nodes are totally ordered. So we've got a sequence of actions that we can perform. It's in a total order. All decision nodes that come before some decision node di are parents of it. So in other words, the agent remembers its previous actions. So in here we can remember the previous actions that we did. And any parents of a decision node is a parent of subsequent decision node. So if we have a decision node and a decision node, then one has to be before it. And if this is a parent of this, then it has to be a parent of this. Okay, this says, if we knew this at one stage for this decision, then we're not going to forget it for this decision. And if this is a subsequent decision, then all of these have to be parents, and this has to also be a parent. So it remembers what it did before. And it's not like this, it's difficult to solve it because then it might do things in order to try and remember things. Like if you have mnemonic, if you remember try and write down, there are funny actions that people do in order to remember things. Right? So here we're just assuming that it can remember things. So it doesn't have to carry out actions in order to try and remember things. Okay. So it turns out that if we relax these assumptions, the problem turns out to be much more difficult to solve computationally. You can model more problems, but it becomes more difficult to solve. Okay. And we'll just assume there's no forgetting. So what should an agent do? Well, what we're going to try and do is to work out what to do at all of these stages, what to do at every, and what the agent should do at any time now depends on what it's going to do in the future. Right? What you do today depends on what you're going to do in the future. The reason you're going to pay attention today is because in the future you're going to write an exam and do something else. Right? If you weren't going to do that in the future, then maybe there's not much point in paying attention. Okay, so now we have this, but what the agent does in the future depends on what it did in the past. So we have this sort of chicken and egg problem of trying to work out what an agent should do at each of these decisions because they all affect each other in the past and in the future. And so we have to somehow be able to work out what to do, how to solve that problem. And so what we're going to do is to denote this notion of a policy. A policy specifies what an agent should do under each circumstance. So what a policy for this node here is going to specify for each assignment, so it's a sequence of decision functions, a decision function for every decision variable, and it's a function from the parents of this decision node into what I should do at this decision node. It's a function from the parents of this decision node into what it should do, and a function of the parents of this decision node into what it should do. So this is all formal gobbledygook, but you might look at it later. So here's the example of this. So here's our simple policy, the simple function before. Hang on, hang on, I'll just. Okay. Whoops, hang on, I'll just go. Whoops. And what did I do there? Ah, that's better. All right. Good. I got my phone to work on there. All right. So, oops. So now we have this policy, and now we have this. So a policy here has got to be a function from the parents of umbrella, into the umbrella. So in here we have the domain of the umbrella is take it or leave it, and the forecast here is either sunny, cloudy, or rainy. So a policy is something like if sunny, then take, else leave. Okay. That's a policy. A policy might be just always take. Take your umbrella. It might be if cloudy, whoops, hang on, what is it? Cloudy, then leave, else take it, or something. So it's a function from that depends on the parents and specifies what it should do. Okay, that's what that says. It's a function from the assignment of values to the parents into the values that you should take. So how many policies are there? How many functions? There's 3 different things it could depend on. So umbrella only depends on the forecast. Right, so does anyone know how many policies there are? Hmm? 6, someone suggested. What else might it be? It's not 6. Someone thinks it's 12. Why is it 12? Because you can have 2 of the forecast variables. Yeah. What else might? Yeah. Hmm? Well, no, here's 3, at least 3 policies. There's 3 different policies. No, there are more than 3. Here are 3 possible policies. No, I said how many policies are there? I'm trying to answer that first question. A policy is a function from the assignments to the forecast into what I should do. And you're suggesting there's only one of them. But there's at least 3. Here's 3 different policies. What? So a policy, there's a decision function for every decision node. And here there's only one decision node, so there's the same number of decision functions as policies. When we get to the next example, we'll have 2 decision nodes, and then they've got to multiply them. Neither of these are right. Does anyone know how many functions there are? How many? 14. Do people know how many functions there are from a set of size n to the set of size m? Is this something you ever learned? No? Okay. All of these are wrong. So if it's sunny, if it's sunny, how many different things could we do? Right, there are two things if it's sunny. And if it's cloudy, how many things could you do? Two. And if it's rainy, how many things could we do? Two. And so we can multiply these together, and we end up with 8. So there are 8 possible assignments of these things. If you have a function from 3 elements into 2 elements, there's 8 of them. There's 2 to the cubed functions from... That's one of these 8. You can specify, you can separately specify what to do when it's sunny or not. You can separately specify what to do when it's cloudy, and you can separately specify what to do. So you can fill in this table. Think of filling in this table. Sunny, and I have a box here, and I can either fill in take or leave. Cloudy, I can fill in this box here of take or leave, and rainy, I can fill in this box that says take or leave. So I get to fill in this box. So if I want to take it if it's sunny or cloudy, then I put take here, and leave here. This says I take it if it's sunny or cloudy, right? And I get 2 choices here, 2 choices here, and 2 choices here. It's useful to know that there are 2 to the cube functions from 3 elements into 2 elements. If you have this function from a domain of size 3 into a domain of size 2. I'm sure you've seen that so many times. We actually did it early in the term, and then it was obvious to you. But okay, so we think about it as this table for sunny, cloudy, and rainy, and you get to choose here whether to take it and leave it for each of these. Okay, and there are each combination. So there's one of them. Right, what's the other one? If sunny, then take, else leave is take, leave, leave. Take all the time is just take, take, take. Right, if cloudy, then leave, else take. It says leave here and take, so it's take, leave, take. Right? Does that make sense? Okay, good. Any questions about that? Oh, you get used to it. All right. Next question. Oh. So this is the same example we did before. How many policies are there? All variables are binary. So one of the ways of doing this, the best way to do it is to think about bi is a function for each test and each result. For each test, the bi function for each test is either engine or drive, and each result, passed and fail, you get to fill in a box. Right, we have this nice graphical user interface of filling this in. And now we have drive, and we have pass, fail, and we get to fill in a box for this. And we also have to work out what to do with the test, and we get to fill in this box. Right, so this is my graphical user interface for filling in policies. How many policies are there? Yeah. Yeah, there's 2 to the 5th policies. For every one of these boxes, I have 2 choices. And I can fill them in arbitrarily. And in fact, when we get to use our graphical user interface in a minute, this is exactly what we're going to fill in this table. Right? When we did this is the table we get to fill in. So this is a way of thinking about a policy. Okay, any questions about that? Okay. So now what we're going to do is now we're going to specify how to evaluate a policy. So given a policy, intuitively given a policy which is just to have a Bayes net is one way of thinking about it. Where we have this as value 1 if these two are true. So if this one here is right, if this one here was, if I filled in yes, yes, no, yes, and I filled in for test its drive. You can think of this now as a probability where this has value 1 if I'm going to do this. This has value 1 for yes. This has value 0 for yes. This has value 1 for yes and 0 for no. And that has 1 for drive and 0 for... And then it's just a Bayes net. Is a nice way of thinking about it. And that's all this says. So remember we had possible worlds which satisfied policies. And the same thing we did before, so this policy is true in this world if the world assigns a value to each decision node that the policy specifies. So when the test was drive, right, and the result was pass, then the policy has got to, you've got to not, by has got to be false. This is by. Okay, and that's all that says. And then the expected utility of a policy is the probability of the world times this, the utility of this world. An optimal policy is the one with the highest expected utility. So that's all it says. All it says is we're just treating probabilities times utilities. And it's just a big table in here. So let's work out, so here's an algorithm for doing this. And sort of like the algorithm we did before, what we're going to do is we're going to compute the expected utility. So we're summing over these factors of all the probabilities times the utilities, and we're going to sum out all the other variables. So create a factor for each conditional probability and a factor for the utility. So we've got all these factors. We're going to repeatedly sum out a random variable that's not parents of a decision node. Whoops. Oops, hang on. Oops, hang on, sorry. All right. So in here, what's the random variable that's not parents of a decision node in here? In this one, what's the parent that's not a... Weather. Where are we going to sum out weather? Okay. Then we're going to select the decision node. One of the decision nodes only going to be a factor with some of its parents. So here we have a factor with umbrella and forecast. We're going to eliminate D by maximizing. We're going to maximize it like we did before. And that's going to return both an optimal decision function and a new factor. I repeat that until there are no more decision nodes, and then we've effectively computed the expected value. So let's have a look at what happens here. So let's go. So here's this decision node. If we go to solve, optimize decisions, we click on verbose. We end up with these three factors, and these are the three factors that you expect. There is the one for the weather and the umbrella, which is my utility. There's this utility function. Whoops. Then there is the prior probability of weather. It's sunshine with probability 0.7 and rain with 0.3. Then there's the conditional probability of weather given forecast. But this algorithm just treats them all as factors. Okay, so this is the probability of the forecast given what the weather is going to be. So what we're going to do is we're going to sum out weather. And then what are we going to end up with a factor on? We sum out weather. So there are the factors. There are my three factors up in the top left. What are we going to end up with a factor on? Yeah, we're going to end up with a factor on forecast and umbrella. And if we do that, we end up with this table here. Right? So this is just exactly the same thing we've done before. So this is with forecast is sunny. Oh, that's interesting. It did the dot, dot, dot. The forecast is sunny, so we've got these three factors we're multiplying together. It cuts off umbrella for both of them. Oh, well. It multiplies these three numbers. So it looks at both the cases of weather as sunshine and weather as rain. And here it's looking at the case where the forecast is sunny and the umbrella is take it. So that's how it gets to 12.95. It's just what we've done before all the time. Okay? So let's fill in this table. What's the up-to policy? What should we do when it's sunny? We can now fill in this table. What should we do when it's sunny? So we should leave it home. We should leave it, right? Why? Right, because when it's sunny, if I take it, I get a utility of 12.95. And if I leave it at home, I get a utility of 49. I get 49. Right? What should I do here? Someone else, what should I do here when it's cloudy? What should we do when it's cloudy? Leave it. And what should we do when it's rainy? Take it, right? So it turns out this is the up-to policy. But the other thing that we do is we end up with another factor. When we maximize, we end up with another factor, and this factor is just on forecast. We're going to eliminate umbrella by maximizing. We're going to get a factor on forecast. And the factor on forecast is sunny, cloudy, and rainy. What value do I get when it's sunny? How much do I get if it's sunny? What value do I get? What do I get? I'm leaving, right? So I'm going to leave at home. What do I get if it's sunny and leaving? What value do I get? 49, right? I'm going to get the value that maximizes it. If it's cloudy, what do I get? Someone else? 14.